Hello and welcome to another video where I'm going to talk about C++ as usual. So today I stumbled upon this blog post from BELAY the C++. I've never read any of his blog posts, but today is the first, I guess. So they have seen some kind of code in their code base that has surprised them, and that is assignment of an R value and binding it to an L value const reference. And they were surprised that this even is a valid program and valid C++ code that actually runs safely. So they've investigated and figured out what uh, temporary lifetime extension is. You can read the blog on yourself. I will link it in the description. It is a good blog. It explains what temporary object lifetime extension is. And there's a link to C++11 standard that adds this feature for R value references. I will also add some other links to Cppref that explains this part of the language, and you can take a look yourself and learn more about it. But today's video's point is more about performance and benchmarking. So there, usually you don't assign your lambdas to const L value references. There is no reason to do so. You would simply assign them to values. You would have an auto myfunc here, const bits bedbreak const auto myfunc, another reference, and then assign your lambda to that value. And then you would simply use that value instead of having a reference here. So there are two scenarios here. There is the one with const L value reference, and there is one with value. And this is the usual code that you would see. Why bother with a bunch of boilerplate like references and stuff like that? That would also confuse the reader. Instead, when you can simply use a value. So they've run their benchmarks and they've come up with some results here that we will going to discuss. So as you can see in the table, there's I'm not going to discuss the O0, O1, or O2, but rather O3, which is something that I'm interested in. So there's like a 10% improvement on O3 just using L value references, const L value references. And on GCC, we're kind of having the same thing. It's not 10%, but it's like 7%, 6.4%. For some applications, these numbers is a lot. Like you're simply changing a value to a const reference, and you're getting some kind of good optimizations. But these don't really make sense. One thing that doesn't really make sense is the actual time that took the result to come up. Like this is a really tiny amount of time that is spent on the benchmark. Let's take a look at the benchmark here as well. We have a vector here, and we're counting the even numbers. So also there's a huge jump from O1 to O2 that is kind of like a magic. So that's one thing that is odd about these results. But other than that, I'm kind of familiar with the language. I know that the optimizer is able to optimize these codes to the same thing because optimizers are not dumb. So these results kind of make me think that there's something shady going on with the benchmark here, which we will get into later. So let's take a look at the conclusion. There's also a benchmark for completion time. I didn't get any kind of conclusive results from these. I think they don't differ much. And later on, we have the conclusion. He first states that these differences are not large enough to make you change your code style. Probably in most cases they are not. And he also mentions that if you have some kind of bottleneck somewhere, you're on your critical path, you're on your hot path, and you want to optimize that path, you may want to use the you may want to use the const L value reference version. And he also mentions that you will have to run your own benchmarks specific to your own context to make sure that these actually are making any differences. So to me, I don't think this is going to make any differences theoretically on any kind of context. So that's something that made me think, why is he getting these results from these benchmarks? So I've actually copied the code, the exact code from the benchmark here to my quick bench here, and there is the 10% that we saw in the results replicated here as well. I have 10% difference here as well. As you can see, this is slower, the plain one, and the const reference one is 10% faster. And you can see that the only difference here is that L or lambda is a const reference here, and here our plain is a value. I've ran this benchmark multiple of times. Some of the times I got consistently constref quicker, and sometimes plain was quicker. Remember that if you want to rerun the whole thing in quick bench, you will have to clear the cache. I'm not going to run it on here on this video because it takes a bit of time. I've run it a couple of times myself. Sometimes I got consistently a constref version being quicker, 10%. But one thing that I noticed is that changing the order of these benchmarks, these functions, did affect the one that is faster. If I run the plain version benchmark first, I would get that plain is faster than const reference, about 10% again. So one theory that I have, that this is actually noise, or things like single core turbo kicking in and then settling down later. So your first benchmark is quicker because of the turbo, and when the turbo settles down, your second benchmark is going to be slower. So also, you can see that these numbers are really low. Like the CPU time is really low here, so there's a good chance for performance. And what do I have to support this? I have actually put these in Compiler Explorer. And in Compiler Explorer, you can see that these two functions that I've declared here. And you can see that actually these functions do nothing. They literally do nothing. They do kind of calls, and then they simply do some kind of prologue for the function calls and stuff like that. Epilogue, I guess this is an epilogue, or maybe a prologue, I don't know, I'm not sure. But these really don't do much here. So, and all over that, you can see that these functions don't differ at all. So the thing is, if I comment these two, I would still get the same result. I've tested this myself. I've commented these, and not even the numbers changed. The numbers stayed the same, and whole thing was the same thing. So I figured out that countif returns a value, and we're discarding that value. So the optimizer can figure out that my lambda here doesn't have any side effects, nor does countif. So it can simply optimize the whole thing. So the compiler was actually removing these calls. So I'm using the benchmark do not optimize. This is a Google benchmark function that you can call on something if you don't want it to get optimized. So I've called this on that, and you can see that my numbers have changed and the differences have disappeared. As you can see, they are literally equivalent, as it should be. So the point to take home from these mistakes on benchmarking is that try to come up and explain theoretically why your code should be faster or should be slower. Here I'm looking at the assembly, and assembly is the same, so there shouldn't be any differences. So if my empirical data is telling me that there should be there is some differences between these. Maybe my tests are not good enough, my experiments are not good enough. So that's one part of the theory that explains why this shouldn't make any difference. The other part is that I'm familiar with the language. Theoretically, the C++ optimizers would be able to optimize both these codes. So I wouldn't trust the empirical test, and I will put my experiments under scrutiny to make sure that my experiments are correct and I haven't done any mistakes and my results are reliable. That's it for this video. If you like this video, put a thumbs up on it. And if you like this kind of content on C++ and programming, make sure to subscribe for future videos. Thank you for watching. Goodbye.